this week about atoms on the periodic table. And then yesterday we moved into talking about ionic bonding. But before we do that, the day before we talked about 4 broad trends on the periodic table. 4 things that we can look at the periodic table and know about trending. Who wants to tell me about one of them?
Atomic radius.
Sure, an atomic radius is a measure of what?
The size of
Good, measure of how big an atom is. And what is the trend on the periodic table?
the more left you go, the larger the atoms get.
Yep.
And the more down you go, the larger the atoms.
Sure, yeah, absolutely, very true. So on the left side of the periodic table, things are bigger than on the right side of the periodic table. Moving down the periodic table, things are bigger than moving up the periodic table. Yeah, that's great. Any questions about that? That feels good. Who wants to tell me about another trend on the periodic table? Another trend on the periodic table. Sorry?
It's in our notes.
Yes, yeah, it is. That's true. You want to go?
No.
No? Okay. Next one I think we talked about was ionization energy. What is that? What's ionization energy?
The ability to gain or lose electrons.
It's related to that, but very specific. It is related to that, very specifically. Lauren? Good. Very good. So to take an electron away from something requires energy, right? Just like when I forget my lunch, so I steal it from Mr. Calford. He fights back. I win, but he fights back. And he's so embarrassed. We just don't talk about it. And he'll deny it if you ask him if it happens. But 3 or 4 times a week, I just take dude's lunch. But I have to put energy into it, all right? You have to work to take something from someone. What's the trend with ionization energy?
The further down the periodic table and periodicity you go, the more ionization energy field.
So as we go across to the right, it gets higher. So it would be harder to take an electron from krypton than it would from potassium. Okay, I like that. So that's definitely one. As we go to the right, it gets harder. What else? Yeah.
As you go down the group,
Mm-hmm.
it'd be easier to take away the electron requires less energy. Like there's hydrogen to I don't know.
Francium?
Yep.
Yeah, so francium will be easier to steal from than hydrogen. Good. And likewise, polonium would be easier to take an electron from than oxygen. As we go down, it gets easier. Okay, what was the next trend we talked about after ionization energy? Yeah. Electron affinity. And what's that? That's also energy. What energy is electron affinity? Yeah, it's the energy involved when we gain an electron. And is that energy that we have to put in? Do I have to put energy in to give an electron to an atom? No, in fact, in this case,
Energy is
very good. Energy is released. We receive energy. Good. And again, it follows the exact same trend as ionization energy. As we move down, we get less energy for giving another electron. You can think of it like the spoiled kid, right? Something like francium, he's spoiled. He's got lots of electrons already. You give him one more, he's like, oh, that's nice, an electron. Like hydrogen, that guy, he's only got 1 electron, right? So 1 more, that's really exciting for him. More to the point, the smaller the atom, the higher the electron affinity, right? And the last one we talked about was electronegativity. By the way, I'm keenly aware that these all sound like the exact same word. I don't make the words. What's electronegativity? Last one. Very good. How strong an atom's pull on electrons is. And that trend, again, the smaller the atom, the greater the electronegativity is the general trend. Good. Any questions about that stuff? I'm going to do little kind of questiony bits about that every day. Make sure we keep it fresh in our minds. It's important. Now, yesterday we talked about naming really, really simple ionic compounds, just binary compounds. Binary meaning 2. A binary compound is made up of a metal and a nonmetal. What can you tell me about what happens in those relationships? What does the metal do? What does the nonmetal do? What do we call these things? Yeah.
Well, metals tend to get a positive charge because
Very good. And once one of them has a positive charge, the other has a negative charge, what happens to them? That's a very good description, by the way. Once they have a charge, what happens to them? That's right. They're held together. They're held together by the force of that charge. That force of attraction holds them together. So an ionic bond is just the pull of opposite charges attracting. You have lots of positive charges, lots of negative charges, and they hold together. Positive next to negative, positive next to negative, so on and so forth. Does that make sense? All right. What do we call the ion that takes a positive charge? Which one's the positive ion? What do we name it? The cation. Good. So the cation is the positively charged ion, which is typically a metal. Good. What do we call the negatively charged ion? The anion. And it is typically negatively charged and is usually non-metal. What side of the periodic table do the cations come from? Good, the left side. What side of the periodic table do the anions come from? Right, good. And we went through all this. I finally yesterday got my act together and put the proper homework up online, only to discover that it was quite blurry itself. But I want to, if I can, get going today with more complicated stuff. I think those ones are probably simple enough for you. I've got a nice sheet, and this one I checked. I printed it myself, and I looked this time. I did this thing where I looked at it, and today's, you know, I had a really good photocopying day today, like really successful. Look, like all the notes photocopied to themselves instead of like that, and all my supplementary handouts, I remembered to hole punch them, which is not a given, and I printed them, which is also not a given. I had a very, very successful day on the photocopier. Yeah.
Will we be learning about covalent?
Yeah, I changed it up a bit, which I have the right to do, but we will, I promise. If you notice there's a 1.5a on yesterday's note, tomorrow you're going to get 1.5b. I decided to talk about covalent after this stuff. I'm not going to talk at all. Tomorrow I'm going to give you like a package to work on yourselves, and you're going to do it, and I'm going to walk around and say things like, good job, you're doing great, and keep going. The lab we're going to do Friday this week, just because my week has been disrupted with my not being here. So the pre-lab's up online. You can start pre-labbing it, but we'll do it Friday, not Thursday. Yeah. Oh, do you not? They're also up here. Like yours isn't in this list. Oh, well, I'll print one for you. Thank you for letting me know. That is weird. Well, you know who you can be? You can be non-existent Michael LeBlanc this week, and I will make sure your name gets added to the assignment list if it isn't already. I don't know if someone grabbed yours or what. There you go. Yes?
For like quizzes and exam, people could bring in the people?
That's a good question. On every test, quiz, and thing like quizzes, whatever, but on every test, I will attach everything to it. So there'll be a periodic table, there'll be whatever charts you may need. Anything like that will be on the test itself. Yep, same thing with the exam. I always print them on there myself.
Okay, I don't want to try to memorize periodic.
No, I could not be less interested in you memorizing the periodic table. I mean, I guess I could be less interested, but I really am not interested. Didn't let you what? Well, the different courses. Those things I want you to memorize for this course. The periodic table is not one of them. But we have a periodic table for a reason. Like, to me, that would be like saying, you're an auto class, but I'm a purist, so I want you to fix this engine, and no tools, guys, bare hands. Like, I just don't see the use of that. That seems like a strange request. Right? Is it? Is it bare-handed?
Like no jack either, you just lift the car up.
I could just get 5 people to lift the car and I'm falling under there. I'm gonna lose that bolt with my teeth if I have to. French, or a socket, or an impact driver, because I can. Likewise, the periodic table is a tool. We're going to use it. It's useful. That's why we made it. And I'm a big believer. Might I add, I'm a big believer in memorizing. Like when I was in elementary school, our English teacher, like we had to memorize a poem every month, right? And then you had to be able to recite this thing from memory. When I was in high school, we always had to memorize a soliloquy from each of Shakespeare's plays. Like every time we studied a play, every act, you'd have to memorize one of the bits. And you still remember them, right? Like 20 years later. So I think memory's cool, and I'm all for memorization. I think it's good, but I think you got to pick your battles. Do I want you to memorize the periodic table? No, I don't. But I want you to know how to use it. Okay. So yesterday we talked about just simple binary compounds, right? And they name easily because you just take the name of the metal, the name of the non-metal, right? If I put, oh, I don't know, lithium and chlorine, what would the name of that be? That's an Li, I promise. Don't be fooled by the fact that it doesn't look like that at all. Yeah.
The name will be lithium chloride.
Lithium chloride, right? We use the name of the metal, we use the name of the non-metal. The only thing we have to remember to do when we name a binary compound is what? Yeah. So this would be lithium, and this is chlorine, but the name becomes chloride. So the naming for those is easy. You should have done a bit of that in grade 9. You should have done a lot of it in grade 10, like a lot, right? What we're going to talk about today, you should have also done in grade 10. In fact, I'm sure you also did it in grade 10. But this one tends to mess people up more. It tends to be a sticking point, which is that yesterday we looked at metals like lithium, beryllium, magnesium, aluminum, zinc, all metals that it's easy to figure out what charge they'll take when they make an ion. Does that make sense? But some metals can form more than one stable ion. Some of the big metals, the heavier ones, can have different electron arrangements that are stable even if it's not a full shell. Does that make sense? Iron does not have to lose 1, 2, 3, 4, 5, 6, 7, 8 electrons to be stable. There's a stable configuration it can have if it loses just 2 electrons. That's stable. So you can have a stable ion of iron that has only lost 2 electrons. And obviously, if it can be stable after losing 2, is it going to keep losing all the way to 8? No, that's a lot of work, right? But you also get a stable ion of iron sometimes under different conditions, 3 electrons. So these are both iron ions that are stable. You know, when I prepped this lesson, that sentence was going to be, are both stable iron ions, and that would have been a better sentence. But there you go. Now, how then do I name with this? Well, we call this ion, and this is very technical. Try to pay attention. We call this iron 2, right? Very technical. What do you think we call this one?
Iron 5.
You know, I said pay attention. This is my only instruction, just pay attention. If you said iron 3 and not iron 5, you're correct. Yeah. Now, I want you to know, you kids are lucky. When I was in school, there's an old system, where whenever something could have 2 charges, you name the lower one with the suffix "ik" and the higher one with the suffix "us." And if you look, like sometimes some schools have old chemical bottles back there, so they would call this ferric and ferrous, and copper would be cupric or cuprous. Yeah, I'm not going to teach you that because nobody uses it anymore. Be aware it exists. It's fine. You might see it on old chemical compounds. Ik is the lower number, us is the higher number. It simply isn't used in modern chemistry. We're not going to learn it. So if iron takes a charge of 2, we call it iron. If iron takes a charge of 3, we call it iron 3. And I put down here a little diagram for you that shows you the key multivalent ions. I do not expect you to memorize this, but you will memorize some of it, just by virtue of using it. I will remember till the day I die that copper takes a charge of 1 or 2. I will remember forever that iron can be 2 or 3. Off the top of my head, I have no idea what gold does, and I have no idea what mercury does. I have to look at the chart. Does that make sense? Some of them you remember because you use a lot. Others we do not memorize. Yeah, so that would be mercury that bonds to itself, and then that combination of two mercuries has a charge of 2+. That's an uncommon pair. It is. Normally, you see that represented as mercury just 1+, but that explains how it actually works. I'm going to give you here the resource that you'll actually have on the test, which is a periodic table of all the ions. And this is a great resource to have. You shouldn't, like, in the long run, you shouldn't need it per se. This is something we should be able to figure out. I think it's a nice resource. Did I give you one? No. There you go. If you look, yes.
When you're making bonds, how would you know which one to use, the plus two or the plus three?
We're going to talk about that. We're going to talk about that.
This one?
So if you look on here, this shows everything on the periodic table and what its most common ionic charges are. You'll see that some of them it doesn't assign any charge to, like boron, carbon, silicon. I think that's it. And some of them it applies more than one to. The way this table is laid out, let me make sure this is true, it always puts the more common one on top. It doesn't put the lower one on top or the higher one on top, it puts the most common one on top. Does that make sense? So if we look at iron, which one is on top? 3+. But if we look at palladium, for example, it has the 2+ on top and the 4+ on bottom. The way it decides which one to put on top and which one to put on bottom is just by how common it is in nature. But you see both of all these. We're going to talk about how we work with that. Well, naming is super easy. The charge the cation takes is just written in brackets next to its name. For example, if I gave you iron 2 oxide, that tells you that it's going to be iron with a charge of oxygen. Great. Now I want you to tell me the formula of that. What is the formula of iron 2 oxide? And take a minute. Take a minute. Let's get everyone to work that out. Sorry? Well, what's the charge on iron in this case? Great. What's the charge on oxygen? Take a look. Take a look.
You needed oxide instead of oxygen.
Of course. Of course, yeah. We always, in an ionic compound, always gets changed to IDE, right? So oxygen takes a charge of -2, always. Oxygen is not polyvalent, right? It's always, always, always -2. So let's talk about this as a group. Iron, in this case, takes a charge of 2. How did I know that iron, in this case, has a charge of 2? It has a 2 in the name. Good. And oxygen, ion of oxygen, oxide always has a charge of -2, right? It's in group 16, which means it's 2 electrons away from having a full outer shell, which means when it has a full outer shell, have a charge of -2. What will this form? How many irons and how many oxygens do I need to charge balance here? Fantastic. 1 iron and 1 oxygen achieves charge balance here. Does that make sense to everybody? Tell me if it doesn't. Don't be shy. We can talk about why. If you don't tell me, I'm just going to assume we're all cool with that from like grade 10. Yes?
Is that how you spell sulfide?
Let's focus. Though you can spell sulfide 2 ways, with PH or with F. Both are correct. But let's, yeah, they're both correct. They are both correct. The British more typically use the PH. Americans more often use F, but both are accepted spellings. Let's look at iron 3 chloride. Actually, this shouldn't be uppercase. I have a bad habit of putting uppercase, but chemical compounds actually aren't, like, they're not people's names, and they don't get uppercase letters, but I always tend to forget that. I don't want to disagree with Merg, so we'll just carry on. I'm right, but we'll move on. If you're starting a sentence with it, then you would capitalize the I on iron, right? But short of that, it's not a proper name. It's just a word. Like you don't capitalize the word shoe because it's your shoe, right? It's just, I happen to name all of my shoes. This is Timothy and Robert, so I mean, the names get capitalized, but that's just me.
For this, does it mean it's like -1? If there's just a...
Yep, that's right. Yeah, if there's just a negative sign, that's a 1. Also, can I give you advice? When you're working, just take this out. That way you don't have to flip. And you can always have it in front of you. I like to work with it right in view. I'll take a look. Okay. Nope. I'll help you with your work after, but I'm focused on this right now. Yeah. Yeah, that's great. Good job. And that makes sense?
Yeah.
Good. Good. Yes. Good. That's okay.
I was just confused because you had a 2 here, so I assumed it was like that E2.
Ah, so what that is telling you is the charge. So let's look here. So what is the chemical symbol for iron? Fe. And in this case, what charge does iron take? What is that 3 telling me? That it has a +3 charge. Now chlorine has what charge? And how would I write that here then? Cl and just negative. Good. If you put -1, that's okay too. Just negative. So now what we have to ask ourselves is, when these come together, if I just did iron and 1 chlorine, what would the overall charge be? If I just take that 1 iron and that 1 chlorine. Like, would the charge cancel? No. I'd have more positives than negatives, right? But I have to get the charge to cancel for this thing to be a nice stable ionic compound. Or do I need more chlorine? What do we think? Yeah, I need 3 chlorines. You don't ever have to draw it out like this, but if I had 3 of the chlorines like this, now I have 3 positive charges and I have 3. Does that make sense? And that gives us an overall charge of 0, which is always what we need for stability. So I need to have, and maybe I could show it like this, I need to have 3 of these. And so the overall formula for this thing will be Fe Cl 3. Good. Let's try a couple more. Let's try copper. Which one do we want? What are my options here? Look at the table. 1 or 2, right? Which one do we want to use? All right, and somebody said sulfide. I don't want to use sulfide this time, actually. Nothing wrong with sulfide. It's a perfectly cromulent option, but I want to say nitride. Copper 2 nitride. This one's a little trickier, and tricky is good. That's how we learn. And did you get the periodic table I just handed out? Yeah. It's actually a nice one for these kinds of questions. And so you're not flipping, you might as well take it right out. Because if you look, it tells you the charge on it. So if we look at copper, it can be 1 or 2. In this case, we're using copper 2. So it's going to be Cu with a 2+. And then what charge does nitride take? Nitrogen.
It takes me so long.
A little bit better at.
I know.
Just repetition.
Yesterday.
You know it's a non-metal because you've got a metal and a non-metal. So the non-metal is going to be up in the top right. Great. So what charge does it take? That's right. And now, like, we're not finding a common denominator. I know. And this is as much.
I know.
You know, but it's kind of like that. It's if this is 2+ and that's 3-. How many of each do we need to get this thing to cancel out? That makes sense. So here's what we can say. If I had just 1 copper, is that enough to cancel out the nitride? So and then now the charge is so here's what you can kind of do. And you'll see some kind of things. You can kind of say, well, if I have one copy, the charge would be. What if I had two copies? That's right. What if I had three? Nope, four of three of that. So three would be six. Yep. And then four, did I say four? And then nitrogen. If I had one, it would be two of them. Three of them. And four. Okay. Now, which of these do you Does it kind of make sense now? Now, 6 matches, and to get 6, I have to have how many copies? How many copies does it take to get 6 plus? Yeah, how many copies do I need? Yeah, how many of them? 2, 4, 6. How many of that? Well, each copy gives us 2 plus. How many of them? Yeah. So how many actual copies is that? So just one of them would be 2 plus. 2 of them would be 4 plus. 3 of them would be 2 plus. So we say 3 copies. Does that make sense? Now, to get 6 minus, how many? One next 2. Good. That's right. Now can I show you a trick? This number and that number. Remember doing that very thing? Now, the thing to be careful with is sometimes right? That's always a good start. As a rule of thumb, you can just switch these understand. You just have to be careful. And I'll give you another one that shows why you're in. Does that make sense? Does that kind of make sense? And what we want to try and do is make sure that so this is 2 plus on 7, then 3 of these and 2 of those. 3 copies is 6 plus. 2 nitrogen is 6 minus. 6 plus and 6 minus together give us. Does that make sense? Okay, good. Oh gosh. Oh, that was standing. Okay, guys. Let's take a look here. How would I write this down below? Copper 2. What's that ion look like? Close. Super close, but it's not CO. That's cobalt. It's Cu. Well, copper is CO. It's just it comes from the Latin, which is cuprous. It's true. And what about nitride? Nitride is the stable ion of nitrogen. And what's its symbol and number? Yeah. Good. Now, how do I get these two to cancel each other's charges? Yeah. Yep. Great. Now, how'd you do that? You're right, of course. Mm-hmm. Yep. So if we have 3 of these, the overall charge would be positive 6, right? 2, 4, 6. And if we have 2 nitrogens, the overall charge there would be negative 6. And those work together to give you neutral. Does that make sense?
Yes.
Good. Yeah. And again, the trick, of course, is that more often than not, you can just cross those numbers across, right? You may have learned the quote-unquote Criss-Cross Rule in grade 10 science. Sometimes, and the next example I'll show you, sometimes it gives you an answer that is correct, but not the best answer. Because just like a fraction or whatever, we need to make sure it's in lowest terms. In other words, if the question gave you like Cu6N4, you'd know, oh, that could be lowered to Cu3N2. Or if it gave you like Fe2O2, you'd be like, oh, if it's 2 to 2, that's the same thing as 1 of each. Does that make sense? We'll talk. We'll talk. That's why I'm nervous. I don't love the Criss-Cross Rule because it does lead to you giving kind of, it can give you crazy answers sometimes. But as a starting point, it's great. And if that's what it takes to get you to the answer, that's fine. You just have to make sure you remember, like fractions, you have to put it in lowest terms. Yeah, question?
Are there any examples where that rule does not work out?
Yeah, well, I'll show you one right now. Well, yeah, right here. Iron 2 oxide. If you cross this down and cross this down, it would want you to say Fe2O2. Does that make sense? Now, that's not a wrong answer. It's true that for every 2 ions, there's 2 oxygens. But the better way to represent that is FeO. Does that make sense?
Lowest terms.
That's right. So if you want to think of it as crisscross it and then put it in lowest terms, totally fine. That works. Of course. You don't have to ask me that, by the way. You guys, I trust you to manage your own bodily functions. Yes, absolutely. The big kids.
Think of it like trying to find the lowest denominator.
Yeah, you totally can. Again, the thing I just want to caution is, I just want to make sure you understand why we do that, like why we do any of this. And the reason we do it is that the positive charges and the negative charges have to cancel each other out, because we know when we pick up an ionic compound, be it salt or be it iron oxide or whatever, it doesn't have a massive electrical charge that shocks us. These things are neutral, and they're neutral because there's always the right number of positive ions of negative charges. And if the way you remember doing that is crisscross in lowest terms, that's great. Nothing wrong with that. Just make sure you understand why it works. Does that make sense? Okay, yes. Yes, that's not where I was going to go, but yes, we can definitely do that.
Other thing, I thought iron involved in nickel has
Ah, so that, on which one it has that?
on the one or two.
That is the old naming system for the groups on the periodic table. Now we just call them 1 through 18, but they used to have 1, 2, and then 3, 4, 5, 6, 7, 8, A, 3, 4, 5, 6, 7, 8, B.
Okay.
These are the B's, and then the blue B is.
Okay. So I was like, blue on this one.
Okay, you care? Okay. No. It's just an old naming system for the periodic table. It is complicated. That's why they changed it to 1 through 18. All right, so let's try this one. Bismuth 5 oxide. I should mention, by the way, you'll see that some, including this periodic table, use Roman numerals instead. I just use. That's more and more what you see. Slowly but surely, science is ridding itself of unnecessary nonsense. So at some point you ask yourself, does it actually make sense to use a Roman numeral, or could I just put the number 5 in there? And then one day we all woke up and said, number 5, that sounds cool. Let's do that. Let me take a little walk around. Yeah, looks good. Time. Good. Good. Yeah, good. Good. Math. Yeah, good. Sorry, I can't see. Oh, yes, I can. I thought it was that sheet. Sorry. Yes, you're doing great. Good job.
I'm gonna try and figure this one out.
Perfect. Yeah, and just make sure you look carefully. What charge does oxygen take? Yeah, you got it. I'll give you some time. Good so far. So now do you know what to do with them?
Are we supposed to make sense?
Sorry?
Are we supposed to make sense?
What? So in this case, 5 and 2 are big numbers, right? But this is where, oh gosh, okay. I regret that. This is where you can say, okay, this is an odd number. This is an even number, right? So it's not going to reduce. So these you can just. Did you take grade 10 2 years ago? Yeah, so it's been a while, right? Okay. No problem there. So write the symbols down here again. And then basically, if these match, then you can just leave them. But do these match? No. So as a rule of thumb, you can take this number and put it down there, and you can take this number and put it down here, if they're not the same number. Does that make sense? And in that case, what number is going to go here? And what number here? And then you always can just quickly check it in your head. 2 bismuth, if I had 2 of these, what would the charge be? 5 each, so 10. And if I had 5 of these, what would the charge be?
-4.
What if I have 5 of them?
Oh.
Right, so that's what we put there. 5 times 2 is?
10.
Good. And now do they match?
Yeah.
Does that make sense? So that's
So
the
if they
idea.
match, then you crisscross it.
If they match already, then you can just put them together and you don't have to worry about it.
Oh,
So if this had been 5 and that was 5, you could just say BI, oh, done, they match.
And if they don't, you have to crisscross it.
That's right.
Okay.
If they don't match, then you can just cross those numbers over, and that works. Does that make sense? Because like here, it's 2 and 2, so they match, so we just put them together. But
Okay.
here, it's 3 and 3. Oh, it's 1. And here we like said, here it's 3 and 1. So now we cross those numbers over. Does that make sense?
Yeah.
Because they didn't match. Here, they don't match, so we cross the numbers over. Here, they don't match, so we cross the numbers over. Does that make sense?
Yeah.
But if they match, you don't have to do anything. You can just put them together.
Okay.
Does that kind of make sense?
Yeah.
Do you want to do one more? Would one more be helpful? Yeah, let's do one more. Oh gosh. Yeah, perfect. All right, so what do we get as an answer for this one? Very good. So 2 bismuth, 5 oxygen, Bi2O5, just like that. Good. So again, that is because bismuth has a charge of 5 plus in this case, oxygen a charge of 2 minus. So if we have 2 bismuth, that's a total of 10 plus. If we have 5 oxygen, that's a total of 10 minus. That cancels. Good. I want to do one more just to make sure we're all in the right place. Let's pick a metal. Let's say, well, that's not multivalent. So no, we're not going to do that. I'm going to say titanium 4. Titanium 4. And I'm going to give you something fairly nasty here, which is just to say this is one of those examples where just crisscrossing isn't going to give you the nicest answer. I'm sorry. You know, teachers have feelings too. Yes, some of us, I don't know. I mean, not me, but I think the other ones. No, I have feelings. I feel things.
You feel the world around you. Touch.
Nice. Good. Good. You doing good? Is he? Good. Good. Good.
Pretty straight in you.
Yeah.
I'm
Yep.
totally sure this is right, but would I just like define this by 2 in order to get to lowest terms? But I think this is the opposite, where this would be.
Yeah, you're right. You were right that you put them in lowest terms,
That's right.
but you have to cross them over as well.
So yeah, so this would be 2 in this one.
That's right. Yep. Spot on. Good job.
Is this just in the same area?
Yeah. Yeah. We're just doing one more.
I thought I screwed up there, but I wasn't sure.
Probably got the season attention.
Huzzah. Good. Can I ask you what your thought process is? Like, how do you get to that?
2 is 4.
So in your mind,
2 is 4.
yeah. So in other words, in your mind, you're just saying
Two
like 2 of these cancels that.
Yeah.
Okay, that's cool. I'm just always curious to see what people are, the way they're processing. Good. Beautiful. That's perfect. May I ask what your thought process was there? Perfect. So you just show them, like, always work. Nothing wrong with that. That's great. Good. Good. Okay, you've done the right work here now, so that's perfect. So how many titaniums? Yep. And we don't need to put a 1. Yeah. And how many oxygens? Yeah, perfect. Yeah, that's right. Does that make sense?
Yeah, now it makes sense.
Cool. Cool. And I promise, the more you do the easier
Yeah,
it gets.
exactly.
I promise. The more you do the easier it gets. Okay, so let's take a look. Titanium takes what charge here?
Plus one.
4 plus. Yep, plus 4. Both are right.
Okay.
Both are. It is actually, this is one of those weird things. It's totally acceptable to write 4 plus up here. Totally acceptable to write plus 4. There's not a hard and fast rule about it. Either is fine. Oxygen takes a charge of -2. Good. So now there's lots of different ways you can approach this. Some people like to say, okay, if I draw 2 of these, that now I have 4 over here, 4 over there. So I know it's TiO2. Perfect. That's a totally legitimate way to think about it. Some people remember from grade 10 and they say, okay, I'm just going to crisscross these down and I get Ti2O4 and then I need to remember to put it in lowest terms, right? And both of those can be divided by 2, which would give us TiO2. Fine, nothing wrong with that. That, to me, is not how my brain works. Sorry? Well, no steps are unnecessary if they help you get there. Whatever your thought process is, that's okay. There's as many ways to think about a question as there are different brains in this room. We all think differently. So don't ever feel pressure to be like, I should figure this out the same way Zach Brown figures it out. Well, Zach Brown's a different person than you are. You may think of it like this. You may go, okay, titanium 4 plus, and if I have oxygen 2 minus, and I kind of think, okay, what if I had 1 of them, 2 of them, 3 of them, 4 plus, 8 plus, 12 plus, 2 minus, 4 minus, 6 minus. Oh, those 2 line up, right? And that means I need to have 1 of the titanium and 2 of the oxygen. You know, those are all perfectly legitimate methods. Whichever of those makes sense for you, that's what you should do. Okay? Does anyone have any questions about how it was? Is there anyone who wasn't able to get to that right answer by any method and is confused by it? Don't be shy. Again, now's the time to ask, because we're going to be doing this thing a million times this close. Shame in not understanding something whatsoever. I don't understand most things. I can't remember where the Tupperware is kept every morning. Every morning I open one drawer. There's no shame in that. Let's just make sure we get it. Then I added a label. Now I look for the label. Point being, don't be shy about not understanding something. That's normal. Just make sure you ask. Make sure you come get help. Okay? I will sit with you. If we have to do 200 of them until it sticks, we'll do 200 of them until it sticks. I don't mind. I got the time. I don't like my kids. Hello? No, don't be sorry. Now, we have to be able to go the other way. If I see CuO, as soon as I see copper, I should be looking on my periodic table and noticing what? Copper comes in 2 flavors. Yeah, 2 different flavors of copper. You got your copper 1, you got your copper 2. How do I know which one it is? Oh, but that's the answer. That's good. I like the answer. But how do I know? How do I know the answer? Yeah. Yes, absolutely. So what my possibilities are, I know that oxygen has what charge? -2. And then I have copper over here. Well, it could either be +1 or +2, right? We don't know which one. Well, looking here, if it ended up being a 1-to-1 ratio, which of these coppers did it have to be? Copper 2. Because only copper 2 cancels that -2. Does that make sense? Now, when we look at a tougher example, we'll look at when it isn't quite this easy to see. But does the principle ring true? That we have to look and figure out which one cancels the charge on the oxygen. Copper 1 wouldn't be able to do that, right? The copper 2 can. So this must be copper, how would I name it? Very good. And by the way, let's remember this. Does that copper mean that there's 2 coppers in this thing? No, it means that the copper has a charge of +2. And that's so easy to say out loud, and it's so easy to remember that when you're sitting here taking the note. And then as soon as you see copper 2 on that first question in the homework, you'll be like, oh, there's 2 coppers. I remember that. It tells you the charge. All the measuring tapes
Went
are
back to
in
its
Tim's room
room.
right now.
Okay,
Yeah.
thank you.
There's what?
Two odds and sulfur.
Well, that's weird. I've seen that before. Man, is that spelling mistake and I didn't even make it? That's amazing. Now let's look at this one. Cu2O. Well, what charge does oxygen take here? What charge does oxygen always take? -2. But now, how many coppers do I have? Oh, I wasn't looking for the answer, though that is the answer. But how many coppers do I have? I have 2 of them, right? Can everyone see that from the formula? There's 2 coppers. So the question is this. If I have -2 charge to handle, 2 coppers altogether, how much charge is each copper handling? Does that make sense? We have -2 charge overall from the oxygen and 2 copper ions. Therefore, each copper ion must have what charge? Well, the nice thing with these questions is there's only 2 possible answers, right? It's either copper 1 or copper 2, right? So, first of all, you can just guess, and you got a 50-50 chance. That's not bad, if only life worked that well all the time. But let's say this. If these coppers were 2+, would that work? Why not? Because if these were each 2+, how much overall plus charge would we have? And only 2-. So that doesn't work. What if it was 1+? Does that work? Yeah, because now the charge cancels. So each copper must have a charge of +1. You have to kind of go through this little problem-solving step. I wish I could tell you that there's some formula we always follow. And I guess we could make one up together. But the truth is, it's just a problem-solving type thing. So what then is the name of this thing? Copper 1 oxide. Good. In my mind with this one, since there's only 2 ions for each, just try it with both numbers. Yes, she is. Sure, yeah. No. That's my new password. Is that my new password? That's my new password. I had to change my password again this week. Every time I have to change my password, I'm useless for like 2 months.
Maybe you should just have the same password, but you add a number to 1, 1, 2, 1, 2, 3.
That kind of defeats, in my mind, the purpose of updating your password regularly. If the idea is to enhance security, because somebody might know your password, they might try changing the last number up to the next number. Just a thought. Anyway, so let's try this one. Fe2S3.
I don't know why, but just take it very I'm over here. I can't help it.
Oh, full class today? I think I do. That's easy.
How?
So what do we think? works. Again, I could teach you some long drawn out process. In my mind, the simplest thing to do is just try them both. If this were 2, what would the formula of this thing be? Then it would just be FES. Is that what the question gave us? No. So can it be 2? No, 2 must be wrong. Hey, if this were 3, what would the formula for this thing be? Oh, so which one must it be? It's got to be that one. Does that make sense? In my mind, that's the much easier way to do it. Rather than trying to teach you some algorithm or something we follow, just put both possibilities there, draw it like this, and ask, which one gives me what the question started with? Does that make sense? And again, once you've done a bunch of them, it doesn't feel so daunting. I remember finding this very intimidating when I first learned it. And then with repetition, it stops being intimidating. And I promise, I didn't get smarter. Only getting dumber. So what's the formula for this then? Or the name, rather. I'm sorry.
Iron 3 sulfide.
Iron 3 sulfide. Good. Yeah, you will see it done with pH. I have this nasty habit of switching back and forth between the two, which I guess is bad. It's better to be consistent. But they're both accepted. They're both okay. And apparently you'll even see it with 2 eyes. But you shouldn't. Where was that? Was that on that periodic table? Isn't that funny? Or maybe that's a thing. I'm going to have to look that up today. Maybe I'm wrong, but I sense it's probably a typo. All right, try this one. SNO2. Yeah. Yeah.
One.
Yep.
SM, and then hydride. Why didn't they be able to use it?
Because it's telling you that the reason it draws it over here is that on this periodic table, they keep all the negative ions on one side, all the positive ions on the other. And because hydrogen is this like very finicky guy, he can behave either way. Yeah. So what I want to walk through this. Sorry. What are the possibilities for SN? First of all, what is SN? What are the 2 possibilities for tin? +4 and +2. Okay. Now, which one of these can we rule out? I always find it easier to rule out the one that doesn't make sense. So which one can we say that doesn't make sense? Ah. Well, if this were 4, I think I like 4. The 2, because if this were 2, yeah, if this were 2, then it would cancel itself out right away, and we'd just get SNO, right? But is that what we get? Is that the question? The question is SNO2. So that can't be it. So it can't be +2. So then it must be +4. Now let's check. Does that make sense? Do 2 oxygens with a charge of -2 cancel 1 tin with a charge of +4? Yeah, that makes sense. So the answer must be +4. Am I going too quick, or does that make sense? It makes sense? Don't be shy to tell me I'm going too quick. Yes? If you're asking a question about the last page, I'm not answering it. Are you about to ask me a question on the last page? Okay, we'll carry on then. What would the name of this be?
Pin, oh wait, yeah, pin
Yep.
4.
Yep.
Oxide.
Oxide. Good. And I broke my own rule there. Good. You had a question.
Yeah. So like if it was just SNO, would you use 2?
That's right. That SNO would be tin 2 oxide. And by the way, they both can happen, and they both do. It's like copper. You can have copper 1 oxide and copper 2 oxide. Copper 1 oxide has like a beautiful bluish color to it. And you see that on the side of buildings that were made in copper once. And then copper 2 oxide is like a rich green. They're different colors. And you see when copper rusts, it makes both of them. You see some of that blue and you see some of that green. So they both happen. Does that make sense? They're both real. Okay. Any questions about that? Okay, then we're going to move on to the last topic for ionic naming, which is what we call polyatomic ions, or radicals. And again, you should have done a lot of this in grade 10. But if you didn't, that's okay. Because again, I can't stress enough. If we just have to slow down and spend 4 extra days on this stuff till we're sure we got it and do some online practice and things like that, then we'll do that. Like, I don't want you to feel stressed. If you find that you can't do the homework, you're not getting the right answers, just come talk to me. Like, we will practice as much as we need to practice because it's a very important skill. But a polyatomic ion or a radical is something like this. Nitrate is an example. And nitrate is nitrogen stuck to 3 oxygens with a -1 charge. I'm going to draw a fake Lewis diagram because I'm not going to draw the electrons in there. Sorry? Yeah, I like this too. I think it's fun stuff. So if you take the 4U chem, we'll learn all about how these happen and how we figure out their formulas and things like that. But this is where, instead of just one atom being the ion is a bunch of atoms mushed together. Does that make sense? And there's a bunch of them. In fact, if you look here, I've given you a table with the most common ones. And they all have their own names. So for example, if you see chromate, you can look at this chart and know that chromate is CrO4 2-. Does that make sense? And if you see silicate, you can look and see that it's SiO3 2-. Does that make sense? So there's all kinds of different polyatomic ions. But the most common ones have their own naming system. The most common ones have their own naming system. And the most common ones are carbonate, nitrate, chlorate, iodate, sulfate, phosphate. Okay, these are the most common polyatomic ions. Have you heard of these before? Do these sound familiar? A little bit? Okay. So here's where the naming system works. These are the most common versions of this, but there's such thing as a version of carbonate that has an extra oxygen. One more oxygen, what would its formula be? Not CO3, but CO4. The charge always stays the same on these. And now the name changes. Instead of being carbonate, they call it, very good, percarbonate. You can also get a version of this with one less oxygen. Halo would be what? Not CO3 2-, but CO2 2-. And it now gets a different name. We name these always carbonate. Good. And it's possible to have a version of this that has one less oxygen still. What would its formula be? Well, what would its name be? Hypocarbonite is correct. Just CO, and what would its charge be? Yeah, still -2. Good. So we do this so that instead of giving every one of these a totally different name that's just random, there's at least some standardization to the naming. Does that make sense? One of the things I'm going to ask you to do for homework is to fill this whole chart out. And I want you to note that I've grayed out the one above nitrate. That's because that one just happens to not exist. So there's no point naming it because it's not real. But the rest of these are real and they have names. So the first thing we're going to do for homework is you're going to fill the rest of that chart out. I don't want to spend time doing that, but I do want to spend a bit of time today just working with naming them. It's the easiest thing in the world. When you have a radical and you name with it, you just name with it. When you have to find the chemical formula with it, you do it just like any other. So let's try some examples on the next page. You're going to fill this chart for homework. We'll look at first thing tomorrow. But let's look here. If I have sodium nitrate, how am I going to figure out the formula for this thing? Sodium nitrate. Well, sodium is just what? Na. And then anytime you see 8, this should be a giveaway that it's a radical. And you should look at your chart to see what it is. All right? I don't expect you to memorize all these per se. We're going to talk about what I do expect you to memorize. But for the purpose of the next bunch of days, we can always check the chart. So what is nitrate? Yeah? NO3. Great. And what are the charges on these? Sodium always has a charge of?
1.
Yeah. And what about nitrate, NO3? -1. Okay. That's nice and easy. So what do I need to do to get these to go together? What's the formula going to be? Very good. That's a nice, easy one. Because +1 and -1 cancel each other out. Does that make sense? Good. Yeah.
At the bottom.
Formalize the plural formulas. Just stick with the question we're on, okay? Stick with the question we're on. Formalize the plural formulas, but we're on this question, not that question. Well, under one of these days, you're going to ask about the question we're actually doing, and that's going to be a great day for me. I'm going to be very excited about that day. Yeah, we'll have a party. Okay, let's look here. Iron 2 carbonate. How would I do this? What's my approach? Yeah.
Figure out like what radical.
Sure. So carbonate. So that's great. And just look it up. Look on your chart. It's on the chart in this note. It's also on the periodic table I gave you. It's all over the place. So what's carbonate? CO. Oh, the charge is 2-. And how many O's are there? Perfect. So like that?
Yeah.
Great. And then what about the first half of it? What do I do with that? Yeah. Yeah, and what's that bracket 2 tell me?
Oh, is it
That's right. Okay. Very good. So I don't have any questions about how we did that. Iron 2 tells us which one it is, and carbonate is CO3 2-. Now, how do these come together? Iron has a charge of 2, carbonate has a charge of 2. Yeah, it's like they're made for each other. I want to try, let's do here, I left you a bit of room. Let's do iron 3 carbonate, just to show how that would look different. If instead of using the iron 2 ion, we had used the iron 3 ion. Give that a try. Oh, you even know that the brackets were so good. Yeah, that's great. I was going to say Merg is great. It's the same. Did Merg teach you 10?
Yeah.
Yeah, no offense, but I was going to praise her, not you. But whatever, we can make it you. That's cool. Yeah, good. And then you're exactly right. And then take
So
three.
3,
Yeah, and then put a bracket around it.
and then it's
How many of them? No.
or -3. No.
Don't worry about charges. We never write charges here because we're canceling the charges, right? But you have it right. You know. I know you know this because you said we need 2 irons. These do we need? Looking up here. Yeah, good. And we put outside the bracket. Does that make sense?
So that just times bracket.
That's right. That means everything in the bracket, we have 3. Does that make sense? So anytime you have to put a number with a radical, we put it in brackets. And I think I made a note about that. I did. Okay, so let's try this. Who wants to tell me how to approach this question? You done great. What'd you do? Very good. Great. Okay, so there we go. Now, when we put these together, how many irons am I going to have? How many? 2. Yeah, very good. Be bold. You're completely correct. And then how many carbonates am I going to need? 3. And what do I have to do with a radical if I'm going to make more than one of them? Yeah, we always put them in brackets. So I open a bracket, CO3, a round. I do care, and they should be round. Square brackets mean something else. And we're going to talk about that lots in this class. So they should be round brackets. Does that make sense? I want to do one more. Yeah, we have time for it just before we go, because it has, in this case, ide. Is this going to be a radical? No, if it ends in ide, it's just going to be sulfur. And what charge does sulfur always take? -2. But what is ammonium? That's a radical. You're going to have to look that up. So you're going to have to look up what ammonium is. And I'm going to see if I remember here. Don't trust me. Look it up. Hey, I got it. Look at me. All right. So now, you will find it on this list right here. And it will be the ones that have a +1 charge, I think, bottom right. So you'll find it on the chart I gave you. You should also be able to find it on this periodic table. So if you look here, it's right there. Or you can find it down here. And what would the formula of this be then?
Bracket, NH4, bracket, 2S.
Very good. NH4 and 2 of those, and just a single S. Very good. So we're going to spend lots of time on this. I want you for homework to fill out that sheet, or this table right here, and then I want you to practice with some questions here. Okay? Questions here. If anyone has Terry Fox money, you can put it here. Up. We'll do that Friday. This is another simple lab, but it's a little more exciting than the first one, I think. I think it's a fun one. Sorry? Not yet. Be patient. I'll give you a hint. We're going to do big reactions when we get to the unit on chemical reactions. Yeah.
Whoa.
It does make sense, right? So I promise reactions are coming. You just have to wait till we're talking about reactions. And then I promise we'll do lots of them. Thank you guys very much. So again, on your way out, some naming ionic compounds practice. I don't want you to be discouraged if you're having trouble with this, but I do want you to come talk to me if you're having trouble with this. Okay? If you find it difficult, come ask for help, please. Lauren, can I